next speaker is Caslav Brukner now. So Caslav received his PhD at actually Technical University of Vienna in 1999. Caslav did his habilitation, but at the University of Vienna in 2003. He has been a Marie Curie Fellow at the Imperial College London. From 2005 until 2007, he was a chair professor at Tsinghua University in Beijing. Until 2013, he has also been an extraordinary professor at University of Vienna. And now since 2013, he has been the director, first the executive and now the scientific director of the Institute of Quantum Optics and Quantum Information in Vienna. And also since 2014, he's been a university professor of the University of Vienna. And yeah, we will hear Caslav now talk about what it is like to be Wigner's friend. Yes.
So thank you very much, Essentia Foundation, also Markus, for this invitation. I'm looking forward to also the roundtable and discussion. I gave the title of my presentation, What It Is Like to Be Wigner's Friend. And this is actually a paraphrasation of another title by Thomas Nagel, What Is It Like to Be a Bat, that he published in the Philosophical Review in 1974. And in this work, he's actually criticizing what he calls, and you see here in the fourth line, reductionist euphoria. He's criticizing reductionistic and materialistic assessment and analysis of consciousness. And in a nutshell, if I may, he argues that what is accessible to me is only what it would be like for me to behave like a bat behaves, but not what it is like for a bat to be a bat. So we indeed can try to analyze in materialistic terms all the behavior of a bat, like eating insects or hanging upside down for most of the time, or even having a sense which is based on ultrasound. But nevertheless, all what this will provide to us is to imagine how it is for us to behave like a bat behaves. And so there is always an irreducible subjective element of consciousness that is not accessible to us. And that's exactly what it is like for a bat to be a bat. Now, I will come to this statement later on after introducing the Wigner's friend and try to make a parallel or analogy to the problem that Thomas Nagel was proposing for consciousness. Now, for the rest of my talk, you will see a lot of that kind of pictures, and this is a simplified and abstract vision of a quantum mechanical experiment, or even experience from the everyday life. So what I will be talking is about an observer. I will be talking about some, if you want, a black box in which inside, abstractly, we can think about having a system or particle, a quantum system. And then there is also a measurement device. That's the way how we actually interact with this world. And all what is finally accessible to an observer is this measurement device. And in this measurement device, we have some, if you want, switches. We can choose to make one measurement or the other. You can think about measuring the spin along X or Y direction, or maybe measuring position or momentum. And then these lamps, bulbs, are actually possibility to see outcomes. So flashing lights in one or the other bulb will indicate one or the other outcome. So we can think about, well, the position was 3 meters instead of 5 meters, or velocity was, well, 1 kilometers per second instead of any other value. Okay, so what I want to indicate with this cartoon is that what is accessible to us and on which basis we formulate our physical theories or talk about quantum systems are facts in a very rudimental, primitive way, like light flashing or click in the photo detector. And at the same level, these are the facts just like any other facts in the everyday life, like a slap in the face, to put it to the extreme. So our statements about physics are based on the facts. Now, in quantum mechanics, and I think that's also a part of the popular culture, we have Heisenberg uncertainty relation, or in other words, a certain epistemic restrictions. So we say that we can't measure at the same time position and momentum of a quantum particle. So an observer cannot observe in abstract terms at the same time both x and y, if we are talking about abstract physical properties. Now, this statement doesn't mean that the particle does not have at the same time position momentum, but just that we as observers, or our means or our observation tools, are not sufficient or are not constructed in such a way to access both properties at the same time. And so we can still hope, or we can still have this picture of an objective world out there, particles with well-defined position momentum, and that we can only observe one or the other property at a time. And so that's what I want to indicate with this measurement of x. So we can put the switch on x, the observer can choose to measure x, and all what the observer in quantum mechanics collects is statistical data, how frequently I get result A, given that I choose x to measure, and this is given always by these conditional probabilities in quantum mechanics. Of course, the observer can choose to measure something else, like y, and then there is another outcome called B, and all what I can statistically then infer is the number, how many times B happens given that I choose to measure Y. Now, this situation of epistemic restriction is not only a part of quantum mechanics. We can think about in classical physics as well. And usually we have a coarse-grained measurements, and we cannot measure everything at the same time. But nevertheless, in classical theories, the observed probabilities can always be understood as marginals of the underlying hidden joint probability, hidden because it may not be accessible. So what it means formally is that we can always assume existence of the joint probability for two possible properties. And the one that we observe in the classical physics, and that's the reason why I have here subscript C, classical probability, can be understood as marginalized over those properties that we don't look at. So for example, Px given Pa given x is observable probability, that what's accessible, and I can obtain this by marginalizing or by summing all what I ignore and don't look at. And in that sense, I can have, for example, for a classical particle, both position and momentum well-defined and a given joint probability. And what I observe then is just marginal probability of that by ignoring one or the other property. And because we can assign these joint probabilities to all conceivable measurements, no matter whether any measurement or which measurement is actually performed, we are talking about objective properties of the system. The mere existence of this joint probability tells us that we can define it without specifying what we will observe, and all our observational probabilities will be compatible with the existence of this joint probability. And therefore, the systems do carry these properties objectively, independently of our experiment, or independently whether we will observe this or not. Now, the situation in quantum mechanics is quite different. And we already heard in some detail about the Bell no-go theorem, no-go meaning something is impossible. And now I will not go into any details. And I will also not be very honest in my approach to that, because there are many assumptions that we heard from Eric's talk, what Bell's theorem presuppose. But I will take here a position, and I will put my finger not on locality, not on the causal structure, but on the classicality that is also a part of Bell's theorem. And so I will take a specific interpretation of Bell's theorem, acknowledging that we can still have other possible interpretations or other possible conclusions from the Bell's theorem. And the one that I pick up here is the statement that in quantum theory, probabilities cannot be understood as marginals of the underlying hidden joint probability. And mathematically, this means that there is no such a probability distribution that the quantum mechanically observed probabilities are seen as marginal of those probabilities. Now, the real Bell's theorem involves more than one observer. It's more complex, what I want to say. But nevertheless, I keep this simple picture just because I want to be at the core of the argument and not to lose myself into details. So what we can conclude out of this statement that quantum theory probabilities cannot be understood as marginals of underlying joint probability, that there is no such joint probability in the first place. Well, one possible route that I want to choose here is that it makes no sense to speak of X when Y is measured and vice versa. So there is no sense to speak about position of the particle per se, independently of the way how we want to observe the particle, or that the properties of particles acquire their objectivity only when they are measured, only then when they become a fact. So if I want to talk about the position of a quantum particle, then I need to measure it, and I have to get a result, like light flashing or a photo, a click in a photo detector, which will indicate which position the particle has. But then at the same time, I should not say anything about momentum because the momentum was not measured. So that's a very deep revision of our notion of classicality, or reality, if you want, as we know from the classical physics and everyday life. But however, we got in the meantime used of it. I mean, if you work in the quantum mechanics, it's shocking, but at the end you accept this. And the idea that we have now is indeed that we should not talk about some counterfactual properties of particles. We should talk only about properties of particles if they are measured. And it's, in a sense, normal then to take the position that if momentum is not measured, there is no meaning to talk about it, and there is no well-defined momentum. But now, we are coming to the Wigner's friend thought experiment that sharpened this and forced us actually to go even to more extreme situations. And here I introduced this, but Eric already did it, and Markus as well, with the idea that now we have encapsulated observers. So there is still this initial observer that I call now Wigner's friend, who makes some measurement on her quantum system and indeed choose to measure X and gets the result. So there is no doubt, or maybe there is, that the friend experienced a definite fact about measuring property X. But because we have such a measurement scenario, this friend is also closed in a box, in a sense, and together with her system represents yet another quantum system that can be observed by another level of super observer, if you want, who is called Wigner. And furthermore, Wigner can measure a different observable than the friend. So what was impossible in quantum mechanics to do it at the same time, we somehow distributed and let friend measures X and then Wigner measures Y. And so we, of course, may ask ourselves to what extent we can trust friend that the friend did this measurement and that the friend does see a definite outcome. And the last version of the Wigner's friend thought experiment was provided by Deutsch in 1985, who suggested a friend can communicate something to Wigner, can communicate actually anything that is not related or correlated with her outcome. Because if the friend reveals the outcome to the Wigner, then the whole superposition would collapse, and basically the friend and the Wigner would have the same description of the whole experiment. But the friend doesn't need to do that. They can communicate about many other things, like what's the weather or anything what doesn't correlate with the outcome observed by the friend. And in particular, the friend can send a message to Wigner in which she informed Wigner that she has performed X measurement and has obtained a definite outcome without revealing which outcome she observed. And that's the beginning for the Wigner to trust friend that not only he himself saw a definite outcome, but also friend saw a definite outcome. And so we have a very peculiar situation in which Wigner measures Y and knows that the friend measures X. Now, back in 2015, I tried to then contrast this situation with what we know from the Bell's theorem and prove something which I call a no-go theorem for observer-independent facts, in which we arrive at the same statement as Bell, that the friends and Wigner's probabilities cannot be understood as modulus of an underlying hidden joint probability. However, the situation is more severe than the Bell's theorem, just like we heard from Eric, because both observers performed their measurement, and there are some evidence that these measurements have been performed, and in both cases, definite outcomes have been observed. And this is definitely a tension, which also have been considered by many people in a refined way, including also Eric's work. Now, what does it mean, this no-go theorem for observer-independent facts? Can we get some more operational understanding what it would mean that this joint probability does not exist, but nevertheless, both observers have seen a definite outcomes? The way how I understand this is the following. The situation that we observe is when the laboratory is closed. But if Wigner decides to open the lab and ask the friend what she sees, her perception at that very moment will be different from the one she had before opening the door. So opening the door is something which is choosing to measure either the same observable as Alice, as the friend, so meaning X, or not opening the box, meaning the Wigner measures Y. So indeed, if you open the box, and that's what I want to indicate with this cartoon, is that her perception or her fact or her result has changed depending on what a Wigner does. And this opening of the door, in certain sense, disturbs the perception of the friend. And this can be done even from the distance. That's something which I don't want to tell you, but that's what you have to conclude after violating Bell's inequalities for a pair of Wigners and pair for the friends, which is the idea from the paper. Now, I now slowly want to come back to what it is like to be a Wigner's friend. There are two situations. One is in which Wigner performs a different measurement than friend, does not open the lab. And in that situation, we have a different prescription of the physical situation. And that's the first time I put a quantum mechanical description of this situation. One would be by friend and the other by Wigner. And what you see here in the first row is what we call entangled state between system being in certain state corresponding to the certain outcome, and then friend being aware of this outcome, and in the superposition or in another amplitude, we have the system showing the spin down, for example, as one of the property, one of the outcome, and the friend seeing this spin down. This state is very much different from the state as friend describes the system, because the measurement has happened for the friend, the outcome has been realized, and the friend sees either the spin up or spin down. Now, what these states of the friend means everything what you can imagine in the laboratory, all degrees of freedom that can get coupled with the outcome, everything where this outcome will be redundantly imprinted or recorded, including maybe the friend's memory. But if we open the box, then the two descriptions will be the same. They will both see one or the other system. It's only, and that was in the previous slide, that by opening the box, the friend's perception before opening and after opening has to change. Because if it would not be changed, then Bell's inequalities will be satisfied, which we believe in ultimate experiment will not be the case, or we can expect this result. Now, if we consider these two situations, they are very different, because the no-go theorem for observer independent facts tells us that before opening the box or the door of the box, we should not consider outcomes of the friend and Wigner as coexisting. There is no joint probability for the two outcomes at the same time. So in a sense, they cannot share the objective facts. What is the fact for the friend? This means the spin up or spin down in X measurement is not the fact for the Wigner, because it's not the same measurement outcome. And also what is the fact for the Wigner, being one or the other result in Y, is not the fact for the friend. So then don't share the same reality if you want. After opening of the door, they do share the same reality. They enter the same bubble, as Eric said, and then you can share the objectivity of the facts or objectivity of the outcomes. And now I'm coming to this, how it is to be like a Wigner's friend. It seems that there is certain analogy with the situation with the bat. And using the same words that I use for description of the situation of bat, I can say that what is accessible to Wigner is only what it is like for Wigner to be the friend, not what is like for the friend to be the friend. And that's refers to exactly different descriptions on the left-hand side. This description by Wigner is a description of the Wigner's friend situation, but this does not correspond to the direct perception of the friend, which is the lower line, equation, the lower line on the left-hand side. Now, one possible way to understand this, and also to think about more general situation, we have a sequence of ever more powerful observers, starting for the friend, and then Wigner 1, Wigner 2, Wigner 3, that all the notions that we know from the quantum mechanics as the notion of the system or quantum state, environment, measurement, unitary, collapse, irreversible, or outcome are relative to observation or observer. Of course, within the box, all observers, through the sense of intersubjective communication, will arrive at the same notions of the system, state, or outcome. But across the borders between these different bubbles or boxes, there is no shared reality. And that's the reason why we start to think about facts, not absolute facts, but relative facts. I don't know how much time I have, because I can stop here or take another couple of minutes, not longer.
You can have a couple more minutes.
I can have a couple more minutes. This will be indeed just
later.
a couple of minutes. Thanks a lot. So I would now like something to address the question, do we need to perform the experiment with humans? And I will not provide any answer to that. But I want to say that the current experiments that we have with a small system, with qubits, with photons, are not sufficient. And of course, it would be idle to do that. And we have done this because that's what we can do. And that's good that we do these things. But if we want to extrapolate from those experiments, the situation, what will happen when we have a good definition of observer and replace this small system with observers, I think that this extrapolation will not be justified. An attempt to do that is already mentioned view of relation of quantum mechanics by Caslav Brukner and other people around him, which tells us that there is no physical difference between observers and small systems. And given that quantum mechanics is universal, which is the pre-assumption of this approach, we could extrapolate the results from small system and basically say that this same happened with the Wigner's friend situation. And I think this is not the case. So it will be ideally that instead of the friend observing one spin, we just have, for example, two spins where one spin, in a sense, observe the other spin, whatever it would mean. However, and that was a statement of a new no-go theorem from the last year by myself and independently also from Jacques Pienard, who will tell us something tomorrow, is that we know that observers' states under the inverted comma of a spin are not really orthogonal to each other. So there is when we say that something is orthogonal in quantum mechanics, that means that perfectly distinguishable states. And perfectly distinguishable states, like the things that we have in the classical world, they can be considered as knowledge because we can copy them and share. And so observing, accessing knowledge has a meaning whenever we have states that are distinguishable between with each other. However, if we have just two spins, the states that we could have assigned to observing one spin, observing the other spin, does not have this property. They are not orthogonal to each other. And therefore, it's very hard to identify them with the states of knowledge or beliefs. And furthermore, every state can be written in different bases. That is what is known in quantum mechanics as basis ambiguity. And so it remains really ambiguous to which base the relative factor refers, because the same physical situation could correspond to different ways of writing these states. And here we will say, whoa, the spin one observed spin two along the vertical direction, whereas in the lower case, it will be along the horizontal direction. So what does the spin observe? All of them, only one of them, and if only one of them, which one of them? The situation with observers, at least as we handle them in quantum mechanics without trying to define what observer is completely different, because the states of the friend or an observer are orthogonal to each other in the preferred basis of the friend's perception, and therefore it can be considered as knowledge. So when we see something has a blue color instead of red, these are distinguishable states, and we model them in quantum mechanics as orthogonal states. And these are the states that have a very preferred basis. And there is no meaning in writing these states in any other basis than in the basis of the preferred basis of the friend's perceptions. So with this, I would like to conclude my talk. And I put here the two short papers that are accessible actually to non-physicists or physicists, but not quantum physicists. And I invite you to look at them if you're interested in this topic. Thank you very much for your attention.
Thank you, Caslav, for the great talk. Quick question right away. So how did you make the postcard from friend to Wigner? It looks so authentic. Did somebody send it to you? Google.
You Googled it.
Google did it. Okay. I was wondering. So yes, how do we go on? So Nuria, is there something you want to comment or ask, perhaps?
Yeah, maybe I need a minute to think a bit how to formulate my question. So if you have one, then go ahead.
Yes, I mean, we could see if we have actually questions from the online audience, which we haven't done so far. Maybe one question from there. Okay, something is typed up. Aha. So the question is, if observers are relational, what are the relations? Are these relations between relations? Okay, maybe this, I think this also refers, Caslav, to a discussion you may have had with Rovelli and with ideas that spins cannot be observers. What are the relations then?
I'm not sure I fully get the question, but are the relations absolute in a sense? If the effects are relative.
And they are relational.
If observers are physical systems and they are relational, that was the question,
Yeah.
then what are these relations? So I also don't fully understand it, but maybe, yeah.
Yeah. I think that I'm not sure I'm answering this question, but I do think that, I mean, I don't see a tension between considering observers as being physical system and yet not identifying the situations between observer and quantum system and on one hand, and the relation between two quantum systems on the other hand. And the difference between these situations is in the notion of facts. And it seems to me that when we talk about the facts, we make commitments or use categories that we know from everyday life. We say, oh, the spin is up along z direction, and we say that's the direction. And so we may use the language that requires certain resources. That is, to have a meaning of the spin showing up in direction, we need to have a direction. It requires a lot of resources that are usually available in laboratory to make these statements. And probably we are bounded to make these statements because we make these statements in classical physics and everyday life and so on. And when we talk about two spins and we want to say, oh, one spin is up along this direction, there is no enough resources in these spins even to make sense out of this statement. And therefore, there is not enough resources to even make a fact. There is also no click, if you want, in a photo detector, and also the meaning of this click is absent in this situation. That's why I feel that we cannot map this one-to-one, although in both situations we can talk about physical systems. I don't know whether it answers the question, but...
Yes, so maybe I jump in here and do a follow-up comment or question. So it seems I do agree with your statement about the spin not being an observer and the relevance of orthogonality of observer states and saying this encodes knowledge about what the observer has seen or experiences or remembers. I just wonder if you can, if you go this argumentation a bit further and then you say, well, what is an observer? It's somehow the collection of classical information that he holds. This kind of undermines the definition in the first place that you point at a quantum system and say, this is my observer. You would have to do a more elaborate pointing. You would have to point out as well a basis, perhaps, or one where you. So I know if I wonder in what sense this is different from just saying a superposed laboratory is not something where I can point to and say, here is my observer. Do you see what I mean?
This is related to your question previous to Eric, I guess. Huh?
It's a bit related. Yeah, maybe I'm repeating myself in some sense because it seems to me a bit kind of a little question mark in all of what we do is here, like, what do we mean by an observer here?
Yeah, I don't know how to. I think I'm trying to identify what are necessary, maybe, but not sufficient conditions for it.
Yes.
And what I want to say that even in that attempt, there is a tension, which I wanted to identify with this question, what it is like to be a Wigner's friend, or what it is like to be observer, and that I think that what you are pointing to materializes in our consideration to the fact that the state that I assign to the observer and the observer to the friend on one hand, and the friend's perceptions are different things. Mm-hmm. And maybe it's not surprising anymore, because on one hand, I'm just I'm thinking about the observer just as a physical system, and then I apply the quantum states, and I actually ignore all the interesting things that distinguish the observer from any other physical system. Mm. And then we have a description of the observer herself, which is different. Mm. This is not now defining what is the observer, but I think that partially this distinction between these two possible descriptions points towards that that there is distinction between having your own description as a subject and being just an object of somebody else.
Yes, I think I agree with this, yes. Great. Now, since we're running out of time, maybe ask Nuria if you want to ask something. We should pass on. Yes. Okay.
Okay. I'll just try to make it very quick. I think it's just a follow-up comment on what you've already been discussing. But is it correct for me to understand that? So, for example, there is a concept of left and right, and this is very intrinsic to human physiology and so on. And for example, I'm very bad with left and right. So as an agent, when somebody asks me, "Oh, show me your left," I first look at my hands and I think, "Oh, okay, I write with this one, so it must be the right." And so somehow this is that the difference that you point out between just being an observer in a sense of observing something and also having this reference system in which as your hands, for example, or I don't know, the DNA helix.
I think this is that the notion of left and right is not available to a single qubit. There is no enough resources again, even to make sense of it, and therefore only something which has sufficient resources, but it's maybe not only that, but it is even able. Only something which has enough resources enable to make statements that we use in our laboratories. Even the position of the particle is X, or it's left from my door, or points towards some direction. These all statements we borrow from everyday life. We use them in classical physics, and then we try to do the same thing in quantum mechanics. And then there are these problems. Distinction between there are problems because you cannot assign even for two quantum systems without having a well-defined lab in one of them. But I think that maybe I would like to think about how to go beyond that. Maybe we can make statements not in these categories, and nevertheless say something without standard situation of the lab and an observer.
Okay, thank you.
Great. So first a comment for everybody who is online now. If you typed up your question and we don't have time to answer it now, we may get back to it later in the panel discussion. So from about 4:30 on, in our time zone here, in half an hour after the next talk, there will be opportunity to ask more questions, and we may also get back to earlier ones that you typed up. For now, let's thank Caslav again for this great talk.